Archiving started.
Good morning and welcome to Part 2 of Chapter 8 on sampling distributions and hypothesis testing. In Part 1 of this particular chapter, we discussed some basic terminology, and you're becoming more familiar with the basic terminology and steps that we will use for pretty much the remainder of the course. So this is a critically important lecture for you to watch and also to read in your textbook. So make sure you've read Chapter 8 before beginning Part 2 of this particular lecture. As you might recall last time, we ended up talking about sample statistics and test statistics and the differences between those two terms. So just as a recap, sample statistics are the statistics that are calculated from an actual sample, and then we use some way, we calculate some numbers, and we summarize or describe the sample. And the way we can describe a sample, well, you've already been exposed to some sample statistics. Think back on our lectures in calculating measures of central tendency, for example, where we calculated means, the mode, and the median. Okay, so those are examples of sample statistics. They're often called summary statistics. And again, it's just a way to characterize or describe your sample. That's different than the actual test statistic. As the name implies, the word test is talking about we're using some type of test, statistical technique, if you will, to determine whether there are differences or a relationship between particular variables of interest. So, again, that test statistic is the statistic that's used in your statistical test. We're going to learn about many different test statistics in this course. One, in fact, you've already been exposed to, and that's the Z statistic. But we also have others that are coming up soon, and that's more commonly used in psychology research. The t-test, for example, the f-test, the chi-square test. These are all inferential statistics. Go back if you don't remember the difference between descriptive statistics and inferential statistics. Okay, so here's an example of having sample and test statistics. Okay, so we have a study, let's say, that's going to be a randomized clinical control trial where we're basically going to compare two treatments for anxiety. Okay, so we're going to have one group that's administered a particular drug to reduce anxiety, and the other is going to use relaxation techniques to mitigate anxiety. Okay, and after treatment, what we're going to do is we're going to obtain each group's mean anxiety rating. So we ask those two groups after they've taken, for example, the drug or used the relaxation techniques for an extended period of time. We ask them to come into the lab and they complete a self-report questionnaire of their anxiety rating. Okay? Then we're going to take the mean of those ratings. So essentially we end up with two numbers. Let's say group 1, who took the drug, reported a mean anxiety level of 16. And let's say that we have mean of group 2, who used relaxation techniques. They had a mean anxiety level or rating of 10. So those are measures of central tendency. We know that there are some pros and cons to using the mean in as an indicator of central tendency. Remember, the mean is a little susceptible to outliers. So we would want to look at the entire distribution of scores. And you can think about what the distributions might look like just based on the numbers that I've given you. So a mean of 16 versus a mean of 10. Okay? So if you can picture those two groups now, the information we've just collected and summarized, that's an example of sample statistics. Okay, so we took some numbers and we computed some basic statistics based on our sample. Okay? Now, what we can use is the group means the levels of anxiety, 16 versus 10, and those standard deviations that are associated with them. So there's more than just measures of central tendency at play here, and I sort of alluded to this earlier. If we actually looked at the entire distribution or dispersion of scores, we could also have our measures of variability. When we take those measures of central tendency and the measures of variability combined, we can use those to compute what's known as our test statistic. And in this case, because we want to compare two groups, again, those who received a particular anxiety drug versus those who used relaxation techniques, the appropriate test statistic in this case would be a t-test. You don't have to know that quite yet. What I want you to understand is the difference between sample statistics and a test statistic. Generally, how we'll handle this from this point forward is a t-test would allow us to compare whether those two groups, whether the level of anxiety that was reported by the two groups, so a level of 16 versus a level of 10, is that difference large enough? In other words, I know you've heard this in many of the psychology papers that you've read, is there a statistical difference between the two groups? Okay. And what we do is we compare our obtained T, and that obtained T is based on the sample statistics. Okay, so we're using those sample statistics, the means, the standard deviations, to compute a test statistic T, that's our obtained T. And we want to know whether that obtained T, okay, is larger than to have occurred by chance based on some known distribution of T. Okay. If it's too large to have occurred by chance, then we reject H sub 0. Do you remember what we call that? That's our null hypothesis. So we're rejecting the null. And we conclude then that the treatments appear to differ. There appears to be a difference between level of anxiety for those who received a drug versus those who used a relaxation technique. If the obtained T doesn't seem to be too large to have occurred by chance, then we do not reject the null hypothesis. There appears to not be a difference between the drug and the relaxation techniques. Okay. Let's talk more about that last part from the previous slide. When do we actually reject the null hypothesis? Okay, so here's some information about that. Even given large effects in our samples, and when I say that, what I mean here is large differences between our group means. We can never be completely sure that our null hypothesis is false. Instead, we set some confidence level. And so we can say with X% confidence, for example, with 95% confidence, I can say that my obtained T is too large to have likely occurred by chance compared to the known distribution. Okay, so there's really no right answer on how confident we must be, how strong must the evidence be to reject the null. Okay, this is strictly based on tradition. And in psychology, we traditionally reject the null if the p-value, that p-value is our confidence level, if the p-value is less than 0.05. Okay, so that's just what we use here. Some people use more conservative estimates and will use p is less than 0.01. So that's more stringent. Okay, that's more stringent. It's more, you have to have a larger difference between your groups, a larger obtained test statistic to find a difference and to say it's likely to have occurred, not likely to have occurred by chance when you have a p is less than 0.01. But all in all, traditionally, in psychology and in many of the other sciences, we use a p is less than 0.05 as our standard confidence level. So I want you to be able to determine whether something is significant and whether we're rejecting the null hypothesis or if we're failing to reject the null hypothesis. We're going to use this decision terminology throughout the remainder of this course as we discuss the t-test and all the different variations of f-tests, for example. Okay. What I want you to know for this particular lecture is if I were to give you a p-value, I would want you to be able to make a decision based on that p-value. So thinking about the bottom of this slide that I'm showing now. If I say P is equal to 0.04, what does that mean? Well, it's less than 0.05. Remember, that is our cutoff value. So P is less than 0.05 in this case. So we are going to reject the null hypothesis in this particular instance. Excuse me. If P is equal to 0.1, okay, that's greater than 0.05 in this case. So we do not reject the null hypothesis, and the typical way to say this in statistics and in our research is that we fail to reject the null hypothesis. Some more about that decision theory terminology. So we're setting some sort of significance level. You've heard me say this already. We're trying to deem whether the statistics are suggesting that there is a statistical difference between particular groups. The formal way of writing this in probability terms is what is the probability of rejecting the null hypothesis given that the null hypothesis is correct. We call that our alpha level. Okay. This is our tolerable risk. In other words, that's our risk of incorrectly rejecting the null hypothesis. So remember, I told you we typically set alpha or our p-level at 0.05. So we're saying that our tolerable risk is that 5% level. So 5% of the time, we may incorrectly reject the null hypothesis. And again, this is based on tradition, and most people are comfortable with that level of risk. I mentioned that a p-level of 0.01 is a bit more stringent, a bit more conservative here. So p-value of 0.01, if we convert that p.01 to a percentage, remember converting our probability to percentage, we're multiplying by 100, so that gives us a 1% tolerable risk. So there's a 1% chance of incorrectly rejecting the null hypothesis. What about a rejection region? That's a new term probably for you. The rejection region is actually the set or range of outcomes on a distribution. Okay, if you can picture that distribution, it's a particular range or an area on that distribution that leads to the rejection of the null hypothesis. We're going to draw a lot of distributions in the course because for those of you who are visual learners, it may help to illustrate for you whether an obtained test statistic falls within a rejection region. Okay? So oftentimes we have these p-values, and that's our significance level. But we can also use test statistics to make determinations on whether there are statistically significant differences in our data. And we will use the latter more often in this course. So when we run a statistical test, there are 4 possible outcomes, and those are listed here. Okay? So if you look to the right, the first column, here we're talking about our decision. So let's say that we look at our obtained t statistic and we compare it to the t distribution, and we determine that we're going to reject the null hypothesis in favor of the alternative hypothesis. If indeed the null hypothesis is true, but we have rejected it, and we've said that we do not think it is true, that's a mistake that we've made. There's a mismatch there between what our data are telling us and what the actual is. Okay, so the null hypothesis is not true here. Not true. This is an error and a mistake, and it's known as a type 1 error. You may think about that as a false positive. False positive in the sense that we said, hey, we found a difference. We're rejecting the null hypothesis, but the null was actually true, meaning there was not a significant difference between groups. Remember, the null hypothesis represents no change. You may recall that from part 1 of this lecture. So we have falsely said that there is a difference in our group. That's a false positive. Okay? And that type 1 error, that's our tolerable risk. Okay? So it's typically alpha. And alpha is equal to 0.05 if we're using that 5% tolerable risk level. Alpha could be equal to 0.01 if we were using that 1% more conservative estimate that some people use. In this course, we will typically use 0.05. So you should always use 0.05 as your tolerable risk level unless I indicate otherwise, for example, on an exam or a homework problem. But if it's not mentioned, you should always use 0.05. Okay? If we reject the null, meaning we found a difference between our groups, and indeed, there is a difference there. The null hypothesis is false. There is a change between the groups. Then we have correctly rejected the null hypothesis here. Okay? And so you can see there, P is equal to 1 minus beta. And beta is what we use to represent power. Okay? All right. The bottom row here. Let's say we do not reject the null hypothesis. We say there is no difference. There is no change between the two groups. And in fact, the null hypothesis is true, which indicates that there is no difference between groups. That's a match. In other words, that's a correct decision. Okay? On the other hand, there is another type of a mistake that could occur here, and that's when we fail to reject the null hypothesis when indeed there was a difference between groups there. This is a false negative. We failed to detect the difference, and that's a type 2 error. The probability of making a type 2 error is what's known as power, and we'll talk a bit more about statistical power in upcoming lectures. Okay, so make sure you can distinguish between the two types of errors that could occur when conducting a statistical test. These concepts are critical to hypothesis testing, and we will use those hypothesis testing steps, as I have indicated previously, throughout the lectures that are coming up. We'll talk about it with regard to using our t-statistic, our s-statistic, and chi-square. Okay, and this is just a recap of the type 1 and type 2 errors. This is in words, so some of you might like it presented in a graphical format as we did on the previous slides. Here, we talk about it in words. So a type 1 error essentially is rejecting the null hypothesis when it is actually correct. Okay, so that was a false positive. I said there was a change, and the null hypothesis was actually correct, meaning there was no change. So I falsely said there was a change as a false positive. Versus a type 2 error, we say that we want to retain the null hypothesis. We think there is no change, when indeed the null hypothesis is false. There is a change. There is a difference between groups. We missed it, so it's a false negative. Okay, now I'm describing to you type 1 errors here in the context of an actual research study. Okay, so think back to our example of watching violent videos and then asking participants to freely associate homonyms. Okay, so we're going to assume that the violent videos really have no effect on association. Okay, assume that. Let's say in the actual study, they had no effect. Okay, so our null hypothesis is true in this case. But assume that we, as researchers, conclude that they do, based on our numbers. Okay, we're crunching some numbers. The numbers indicate that there is an actual difference here. Remember, again, that's a type 1 error. How frequently could a type 1 error occur? That's what we set our alpha level to. It's our tolerable risk. It's our significance level. And again, we traditionally set that at 0.05. So the probability of making a type 1 error is 0.05 or 5%. A type 2 error in the context of research, let's assume that the violent videos really make a difference on the number of free associates. But assume that we, after crunching our numbers, concluded that they don't make a difference. Well, we missed it. We failed to detect it. A false negative. This is a type 2 error. And the probability, again, is denoted as beta. It's difficult to set beta. It's not as easy as the alpha where we say, okay, our tolerable risk is 0.05. Instead, there is a way to set your power or to maximize your power, and that's what you want to do. You want to maximize power. Okay, and power is 1 minus beta, so it's the probability of correctly rejecting the false null hypothesis. So obviously we want power to be high. We want to be correct in our outcomes of our statistical tests. So a high power level is good in research. Critical values. Okay, so I'm sort of going through that list of those critical concepts that you must know for hypothesis testing. Our critical values, they represent the point at which we decide to reject a null hypothesis. So it's the point at which we say any number that we obtain that goes beyond that critical value means we're going to reject the null hypothesis. It means they're going to fall within that critical region. Okay, so for example, we might decide to reject the null when p is less than 0.05. So our test statistic does have some value if p is equal at 0.05. We reject when we exceed that value. And that value is the critical value. So I told you there is some relationship between p-values and our test statistics. In this course, we will use the test statistics to make these decisions. So essentially what we're finding is, what is the critical value? What value is associated with p is equal to 0.05? Once we find that number, and this is the number based on this distribution, it's often based on characteristics of our distribution, such as the sample size, but once we've determined this is the cutoff value for my known distribution, then if that value represents p is equal to 0.05, anything that exceeds it, okay, is going to be less than 0.05. We're going to reject the null hypothesis if a value exceeds the critical value. We can use one or two-tailed tests in our hypothesis testing. Okay. A two-tailed test, think about your distribution. Okay. Think about drawing just a normal distribution. Well, it has two tails. Okay. So we can decide to look at both of those tails. So what that means is, if we reject the null hypothesis if the value we obtain is too extreme, meaning it falls in either tail, in either direction, at the top of the distribution or at the bottom. Or if we have some a priori hypothesis, meaning we would expect only the value to exceed at the top of the distribution or at the bottom of the distribution. Then we can use a one-tailed test. And there are reasons why a one-tailed test is stronger or more powerful than a two-tailed test. Remember, we have a p level set at or an alpha level, set at 0.05. So when we use a two-tailed test, we then split that alpha level into both tails. So essentially we put 0.025 in the upper tail, 0.025 in the lower tail. Whereas with the one-tailed test, we put all of that into one tail. So all 0.05 falls into one tail. Okay? So it's easier to detect a difference with a one-tailed test. You can have a less extreme number in order to do so. However, there are drawbacks to using the one-tailed test, and that is a one-tailed test could miss a surprising finding. Like, so if we expected the value to be extreme on one particular side of that distribution, let's say at the top end, but instead what our data reveal is that the extreme falls on the other end of the distribution, we would totally miss that, because we must decide on whether we're using a one-tailed or a two-tailed test before we even collect the data. Okay, so we don't actually fish around and see what we've got after that's exploratory, but we come in with some a priori hypothesis about what we would expect to find, and that will dictate whether we're going to use the one-tailed or two-tailed test. Okay, here's a visual or graphical illustration of the critical region. So I talked about the critical region. Again, that's the set of values of the test statistic that cause a rejection of the null hypothesis. So this entire blue shaded area is what's known as the critical region or the rejection region. The actual beginning of that spot, I just drew a black line there, okay? The actual beginning of that region, that's the critical value. So that's the point at which anything from it and that exceeds it would be rejected. Okay, so the value that's associated with that particular point, I'm drawing it in red now, with that particular point on the distribution, the p-value associated with that is 0.05. We're going to reject if it's less than 0.05. So anything that falls beyond it or exceeds it. So anything in that blue region. Okay? And would this be a one-tailed or a two-tailed test? Okay, well, the entire critical region here, shaded in blue, falls in one tail. Okay, it falls in one tail, just on one side. So therefore, it is considered a one-tailed test. Okay, you could just see one tail there. The tail, or the one tail that you're particularly interested in, can fall at the top of the distribution as well. And just here's an example of that. We still see a one tail that is actually shaded in here. That's our critical region. We could also have a two-tailed test where we split that critical region into two parts. Okay, so in other words, if a value falls, if our obtained test statistic falls in either of these shaded areas, we would reject the null hypothesis. So we can either be an extreme value at the top of the distribution or at the bottom. Okay, let's talk about a one- and two-tailed example in the context of actual research. Let's go back to our violent video research that we've talked about. So one-tailed test, an example of that would be that we reject the null if the violent video group had too many aggressive associates. Okay, and the key word here to illustrate to you that this is a one-tailed test is too many. So here we're indicating some particular direction. We're talking about only one part of the distribution. It would look, if we were to graphically illustrate this, it would look something like this. So we're saying our critical region is at the top of the distribution. That if our obtained t-statistic shows that people had too many free associates, they fall in the top end of the distribution, in this tail here that's shaded in blue, that we would reject the null hypothesis. A one-tailed test with regard to this particular research study might actually make sense, because we probably wouldn't expect people to show too few after watching a violent video. Okay? So there would probably no need to guard against finding something in the bottom. Okay? We wouldn't expect to find anybody at the bottom of the distribution here. So a one-tailed test might be a logical choice in this particular example. A two-tailed test would simply be interpreted as we would reject the null if the violent video group had an extreme number of aggressive associates, either too many or too few. So there we're really talking about both tails, too many or too few at the bottom. My circle didn't really work out for me there. There we go. Okay, so if they fell at either end, then we would reject the null hypothesis. So that's an example of a two-tailed test in research. You might recall from our standard normal distribution, okay, that the area under the curve is equal to 100%, so that total area, and we know that things that fell about 1 standard deviation below and 1 standard deviation above, that encompassed 68% of the distribution. So if we were to just sum 34 and 34 that's associated with that, there we're talking about 68% fall within 1 standard deviation of the mean. The mean is at the very center. It's our measure of central tendency. Remember, we can indicate that by X bar. If we go 95% within, so that's 2 standard deviations within, okay, that's encompassing everything but 5% of the distribution. So essentially we're taking the middle portion here that I have circled, everything except for what I'm going to circle in yellow here, everything except these little tails on the end. Okay, and because everything is balanced, it's sort of a mirror image, what percent falls into just one of those yellow circles? What percent of scores fall just in that one little tail, if we had a one-tailed test here? Or if we just considered one of the tails, let me say that. Okay, so we know we have 5% left. 95% have been accounted for. So if we had 5% left, we would split that. Remember, so we would say that there is 2.5% in one yellow circle and 2.5% in the other yellow circle. That's our remaining 5%. So essentially, when we set an alpha level at 0.05, what we're essentially saying there, okay, what we're essentially saying is we're looking for extreme values that would fall just at the 2.5% level in each of those tails. So that's when we have a two-tailed test. If we were only interested in looking at just one side, we can put all of that 5% that's left into one tail. So then we would look at 5% just on one end of the distribution. Okay, so just to recap, one and two-tailed test. A one-tailed test rejects the null only if the result falls in one tail. Okay, so we're essentially ignoring the other tail. We have some a priori hypothesis about what we would expect. So, for example, with the violent videos, we wouldn't expect anybody to have too few or be at the bottom end of the distribution. So it made sense to include a one-tailed test because, again, one-tailed tests are superior to two-tailed tests in a couple of different ways. Okay, they're more powerful because we're able to put the entire alpha level, that entire 0.05, into one tail. Yeah, we consider these to be directional tests. So when we state our null and our alternative hypotheses, we talk about direction. We say that we would expect the mean to be greater than or equal to 21. That's the null hypothesis. And our alternative, and these are just arbitrary numbers here, okay, guys? Our alternative is that it's less than 21. So you can see that less than. We're indicating which tail we would expect those extreme values to fall within. I will state, however, even though one-tailed tests may be a little more powerful, they are relatively uncommon in psychological research. It's usually preferable to use a two-tailed test, because oftentimes we have surprising findings in our research, and we would miss these entirely if we didn't use a two-tailed test. And we might find something opposite to our predicted direction, so we tend to use a two-tailed or a non-directional test. So here, when we state our null and our alternative hypotheses, we simply state what our null hypothesis is. The mean is equal to 21. And our alternative, I'm having trouble with that word, guys. Alternative hypothesis is the mean is not equal to 21. So it's different, the opposite of our null. Okay, and again, we reject the null if our result falls in either tail, upper or lower. Okay? So now you have a comprehensive look at hypothesis testing and sampling distributions. We are going to use those hypothesis testing steps, as I have indicated, many times throughout the course. So you're going to want to really bring yourself up to speed and make sure you understand all of the terminology that was described here. If something seems a bit confusing to you at this point, now is the time to bring it up. We're here to help you. So post to the discussion board or email me or your TA within Blackboard, and we are happy to assist you with your request. We want to make this course what you want it to be, so we will tailor it towards your needs. We can make those live sessions with the TA exactly what you need. You just got to tell us what you want. Okay? I posted these suggested problems last time. You should be able to work through all of them. If you're struggling with one or you would appreciate us working through one, just let us know, and we're happy to do so. All right, thanks, and have a great week.